Thank you for the introduction and thank you for the invitation and for the organizer to this nice conference. So I'm Xiao Yuan from the University of Oxford. In fact, they invite Simon Benjamin, my supervisor, but he's super busy right now, so I just come instead. To be honest, I just started 3 months ago, so I don't have many new and interesting stuff to share with you. But today I will also talk about some recent results by my colleagues and also some recent findings by myself. So hope you will be interested. As you can see, I will talk about error mitigation for shallow circuit, in fact, and also its application in quantum chemistry simulation. So here is online. First, I will talk about the motivation and then discuss the error mitigation. And then I also quickly review chemistry simulation. And finally, I will combine error mitigation and chemistry simulation. Okay, here is a roadmap for fault-tolerant quantum computing. So here, so here you can see the threshold for the two-qubit gate is 99%, and you can see now for the systems. Probably you cannot see this. I cannot see. Yeah. So you can see that for all the 3 systems now we can already achieve this threshold. And especially for the ion trap system by laser control, we can already get 99.9% fidelity. And also for the other 2 systems, superconducting and the other ion trap system, we also have a quite nice fidelity. This graph is from the NKIT website, where I think you can also find some more interesting stuff. Speaking of NKIT, so Simon asked me to add these slides to you to introduce the NKIT program. So I just read through these slides. So NKIT is the networked quantum information technologies, and it is the largest of the 4 UK national quantum tech hub, and it is started at the end of the 2014. And we have a lot of money, and we have Oxford and many nice universities and also companies. And I think the goal of NKIT is to create a modular quantum computer. That means we can make some very small-sized quantum computer, which we have a very high fidelity, and we can make many that kind of modular quantum hardwares, and then we connect different quantum hardwares using quantum optics. So here you can see a schematic way to do this. And also we have many experiment groups in NKIT. Here I just mentioned some recent progress of the Oxford team, and you can also find other progress from the NKIT website. So for now, we have get very high fidelity for quantum gates, especially for the 2-qubit gates. We have 99.9, and for 1-qubit gate, we can just get probably just a perfect gate. And also, we can apply gate between 2 different species of atoms in one trap, and we can use very cheap microwaves. And quite recently, they also achieve very fast operations. So now the operation time is 8 orders faster than the decoherence time. So please don't ask questions about these slides. I don't know. So if you want to know more, please visit NKIT or ask Simon. Okay, so from the experiment side, it seems very promising. So we have a very accurate quantum hardwares. But in practice, to realize a fault-tolerant quantum computer, still there is a huge overhead to implement logical qubit with a physical qubit. So here, let's take a very quick example at the Shor's algorithm. For example, if we want to factorize 1,000 bits, then we need 6 million, at least we need 6 million physical qubits to realize this. This graph is from this paper where I think he's also in the audience. If you are interested, you can also ask questions about this, this graph. And so 6 million qubits, I think it's promising probably in 5, 10, or 20 years. But before that time, can we do something without error, without fault tolerance? So one solution is called the hybrid algorithm. So the hybrid algorithm is a combination of the classical and quantum computation. So the algorithm is divided into two parts, where one is solved by, the easy one is solved by the classical computer, and the hard one is solved by the quantum computer. So here, let's take an example. Here we have a quite small sized quantum hardware, and it is also a quite shallow circuit, where each gate is controlled by a few parameters. So for each round of the algorithm, we use some parameter setting, and then we run it, we perform some measurement. And then based on the measurement outcome, we can update the parameter according to like the gradient descent or any algorithms. And then with the updated parameter, we can run the hardware again and again to achieve some goal. So here, this is a combination, it's a quick example of the hybrid algorithm. So I get these two graphs from this paper, where you can also find some quick, brief summary of the hybrid algorithm. Of course, recently there are many works about hybrid algorithms. So it seems that, so here, for the hybrid algorithm, of course, we can use quantum error correction to correct errors. But remember that we have a huge overhead to implement the logical qubit. So instead, how about we don't implement quantum error correction? Then can we still get some accurate results? Then this talk is about how to mitigate errors for this kind of a shallow circuit. So one method I will introduce is called error mitigation. What I will talk is mainly about digital quantum simulation, while the previous talk is about analog quantum simulation. So for example, let's consider a process, quite general process, where we have a state roll in, and we apply several unitary gates sequentially, and then we perform some measurement. Note that the information is encoded in the measurement outcome, that is the measurement probability, instead of the measurement outcome we get. So we have many examples for such cases, like the phase estimation, swap test, also hybrid algorithm. While we also have some other algorithms, such as the Shor's algorithm, Grover's algorithm, where the result is encoded in the measurement outcome instead of the measurement probability. So here we just focus on this type of computation. Then for the output state, if we have no noise, we can get a noiseless state. But actually, in practice, what we get is a noisy state. Then the error mitigation problem is to infer the noiseless measurement outcome from the noisy measurement outcome. In fact, there are a few error mitigation methods. The first one is called error extrapolation. This method works quite interestingly by deliberately making the noise worse. So let's see how it works. So first, let's consider linear extrapolation. Consider for simplicity that the noise channel is a stochastic channel. That is, the error only happens with a small probability epsilon I. And then we can expand the noisy value by ignoring higher orders of the noise rate. And suppose in experiment, we can make the noise worse. That is, we can increase the noise. Then we can get another noisy measurement outcome. Note that here the noisy measurement outcome is a linear relationship to the noise rate. So it is quite natural to have an estimation of the noiseless value by using linear extrapolation. So here, linear extrapolation works by assuming that the total noise rate is not high, such that we can ignore higher terms of the noise rate. And in practice, we can also convert an arbitrary noise model by using the Turing technique to the stochastic noise model. So that is, we can just add extra Pauli matrices before and after the gate to get accurate to convert an arbitrary noise model to stochastic noise model. And also, if we cannot proportionally increase the noise rate in experiment, we can also randomly add extra Pauli matrices to increase the error rate. And furthermore, we can also consider to use more extrapolation points to get even more accurate estimation of the noiseless value. And this method is proposed in both these two papers, where the first one is by my colleague, while the second one is by the team here in IBM. For the first one, they also propose another simulation method, while the second one, they propose two error mitigation methods. While the other error mitigation method is the negative probability, which we will discuss very soon. But before that, I will discuss something more, which is called exponential extrapolation method. So here you can find a new batch. So here, so if you found this new batch, it means that this is a new result, so new recent results. So remember that the noise value can be expanded in this way. Here, pk means the probability that k errors happen in the circuit. So here we still assume the stochastic model. And zk is the average measurement outcome when we have k errors. So here n is the number of gates and r is the error rate. Here, for simplicity, we assume that the error rate is for every gate is the same. And then when n is large and the total number of error rates is a constant, we can convert the binomial distribution into the Poisson distribution. That is like this one. So you can see that the probability pk is proportional, is exponentially decreasing to the error rate. Then it is naturally to have a guess that the noisy value is also exponentially decreasing to the noise rate. Then instead of linear extrapolation, we can also try exponential extrapolation. So later I will show simulation results of the linear and the extrapolation, exponential extrapolation method, but before that, I will also talk about the other method introduced by the IBM team, which is called the negative causal probability method. The method is essentially is to synthesize the unphysical inverse of any noise channel. So here, for simplicity, let's just consider one gate and one noise. Suppose that we consider the depolarizing noise channel, and then we can easily find the inverse of the channel by just solve the equation. And then we can also write it in a more elegant way. Here, P1 means the probability that we do not affect the state, while P2 means with P2 we apply some random Pauli matrices to the state. But unfortunately, here we have a minus sign. So this minus sign generally prevents this channel to be physically realizable. So we cannot realize it in practice. But we should remember that instead of realizing the inverse channel, what in practice we need to do is to get the noiseless value. So here we denote the noiseless value as O and the noise value as O prime. And then the negative probability method works as follows. So with the probability P1, we add nothing. So we just add identity channel to identity operation to the state, to the process. And then with the probability P2, we randomly add X, Y, Z operations to the process. Then in total, we will get 4 measurement outcomes. And according to the form of the inverse channel, it is natural to get a relationship between the noiseless value and the 4 noisy value. So in practice, what we need to do is to rerun the circuit many times, while for each time, we randomly add some extra gates, while in total, we can get the noiseless value from the different noise values of the different runs. This paper is introduced in the IBM paper, where they also consider some other noise channels. While recently, our colleagues, my colleagues, they also consider to extend the IBM work. First, they generalize the result to a general Markovian noise model. So in general, we can use a basis to decompose the channel. And of course, we can also decompose the inverse channel. And then we can use this basis to cancel any local Markovian noise. And furthermore, we can also cancel any multiple qubit gate by just tensor producting the basis. Another problem is in the negative probability method, we need to perform a process tomography to apply the probabilities. But in practice, we may also have imperfections in the process tomography. So we may also introduce errors from the process tomography. But fortunately, as we just focus on the average value of the measurement outcome, we can apply the gate set tomography method to eliminate these errors in process tomography. So next, I will show some numerical simulation to compare these three, in fact, error mitigation methods. The simulation is a swap test simulation using 16 qubits. Here, the swap test, in general, is to evaluate the fidelity between two states. Here, the two states are the CAS state and the ground state. So the preparation of the realization of the swap test is shown here, where the first qubit is the ancillary qubit. It is first realized in the plus state, and then we apply control swap operation on the whole system, and then we measure in the X basis to get the outcome. So the fidelity between these two states can be obtained from the measurement of the ancillary qubits. Here we choose a very naive decomposition of the control swap operation, while in practice there may be some better, more efficient decomposition. In the simulation, we'll assume that the noise happens before, after every operation, and we assume that the recovery operation is applied after each gate, and also that we assume the noise also occurs in the recovery operation. So here is the simulation result. We consider two different noise models. One is inhomogeneous error, while the other is a leakage error. So in an inhomogeneous error, the probability of having X, Y, Z errors is 0.1 is, and the other is 0.006. And so why we choose this probability? This is because this error rate is what we can achieve currently in experiments. While in fact, we assume the error rate for any any gates. So, but while remember that the fidelity for single qubit gate is very, very high. So this is even more pessimistic. So from the simulation result here, we have three different values. While the orange one is the result without error mitigation, the blue is the result with the linear extrapolation, while the green is the result with the causal probability method. So remember that the fidelity between the CAS state and the zero state is 0.5. So what we should get is the exact value of the measurement outcome should be 0.5. So we can see that the result without error mitigation is very far away from the true result. So it deviates a lot from it. While the linear extrapolation works slightly better, so it indeed makes the result better, improves it a bit, but still the prediction of the linear extrapolation is still not that good. While for the causal probability method, you can see that the mean of the histogram is just 0.5. So it says that it worked quite well. So here we consider 1,000 samples for each experiment, and we repeat 100 steps to get this histogram. But in practice, you can use more samples. Then the variance of the estimation will be much smaller. Here we also compare the linear extrapolation and exponential extrapolation. We use the same experiment setting, and the result is shown as this one. So you can see that although the linear extrapolation doesn't work well, but quite surprisingly, the exponential extrapolation works quite well. So finally, we just combine the results into this one graph. Here, the red bar is the result by exponential extrapolation, while the green line is the result by quasi-probability method. So you can see that for the inhomogeneous error case, the quasi-probability method works slightly better because the variance is slightly smaller. While for the leakage error case, the result is different, where the exponential extrapolation method works better, while the quasi-probability method works slightly worse. But you should be careful that the range of the x-axis is different. So in fact, for the leakage error case, the negative probability method doesn't work that worse. So the range of the x-axis is different. Okay, so from the simulation results, we can see that error mitigation works quite well, at least for this medium-sized circuit. And then we go to the next topic, which is chemistry simulation. First, let's have a quick review about chemistry simulation. Here, we just focus on the ground state energy of molecules. Here is the Hamiltonian of the molecule. And in general, to solve the ground state energy of this Hamiltonian, it is hard in classical, using classical machine, while with the quantum mechanics, we can either consider first quantization method. That is, we just discretize the space, and then we directly implement the space wave function. But for this first quantization method, we even need a lot of qubits for even a very small molecule. So it is not very efficient. While more efficient method, probably for small molecule, is the second quantization method. Here, we just choose the energy basis for each atom, and then we can convert the Hamiltonian in the first quantization to the second quantization. So with the second quantization Hamiltonian, we can use some fermion encoding method like Jordan-Wigner or Bravik-Naive method to convert this fermion Hamiltonian into a qubit Hamiltonian. So here you can find a recent review about chemistry simulation. So then essentially what we need to do in chemistry simulation is to find the lowest energy of a qubit Hamiltonian. There are also two methods. One is called phase estimation. The method works by first preparing a state phi that is close to the ground state, and then by using annealing, and then we apply phase estimation to prepare the true ground state. This method is first proposed in this paper. While another proposal which is quite popular recently is called the variational quantum eigensolver method. Here we just try an ansatz state by preparing the state by applying some operations that is controlled by some parameters. This is quite similar to the circuit that we discussed at the beginning of the talk, the hybrid algorithm. So we apply some unitary gates where each gate is controlled by some parameters. We also have several ansatz for the variational eigensolver method, while the target is to minimize the average value of the energy by using, for example, gradient descent method. So the first realization of the variational quantum eigensolver method is in this paper. Okay, so next we just jump to see the combination of error correction, error mitigation, and chemistry simulation. So first, let's see the case for the simulation for the hydrogen molecule. The hydrogen molecule in the minimum basis is a two-qubit Hamiltonian. In fact, where here the coefficients are dependent on the distance between the two atoms. And the trial state of this Hamiltonian is as this one. So I just copy these results from the recent PRX paper by the Asperger-Guzing and the Martinez team. So here, this is also their realization of the trial state, and the right is the result of the ground state energy of the hydrogen. So here they compute both the two methods, variational quantum eigensolver and the phase estimation, you can see that variational eigensolver works slightly better, much better than the phase estimation method. But still, if you can see, still we have some errors in the variational quantum eigensolver method. So this means that the experimental noise in the circuit still affects the ground estimation of the ground state energy. Then we just consider to apply the error mitigation method to the simulation of the hydrogen molecule. Here, suppose that the noise in the simulation is a depolarizing noise channel. In general, it works for arbitrary channel. And suppose that the error rate for a single qubit error is the same, and for two qubit gate is also the same. Here is the simulation result. Here we assume that single qubit error is 0.0005 and two qubit gate is 0.005. So maybe you cannot see very clearly because both the two results with and without error mitigation are quite well. So here is a detailed graph of this one. So you can see that for the result without error mitigation, we do have some mistakes of the estimation of the ground state energy estimation. While with error mitigation, we can reduce the error quite a lot. Here, we also simulate the result with a larger error case. The single qubit error is 0.005 and the two qubit error is 0.05. So this is the So here you can see the result with error mitigation improves a lot compared to the one without error mitigation. While it was to mention that here we use the same sample size for both methods. That is, we just use a 1 million sample size for both the error mitigation and the conventional method. And we just use 2 extrapolation points. In practice, we can also use more extrapolation points to improve the result. So we also consider the case of, about the simulation for the helium-hydrogen molecule. Here is the Hamiltonian, and here is the realization, the circuit, and the result from this paper. So you can see the noise in the circuit indeed affect the simulation result. While for our application of the error mitigation method, we consider the same depolarizing channel, but now instead we have 6 parameters to optimize. And here is the simulation result, where you can see here we assume single qubit error is 0.001 and two qubit gate is 0.01. And you can see that the result with error mitigation is quite accurate. So from these 2 results, we can see error mitigation indeed works for quite shallow and small-sized circuits. But in practice, what quantum chemistry is attractive is because we can indeed achieve very accurate estimation of the ground state energy. But in practice, to achieve accurate estimation of the ground state energy, we need to consider more complicated bases. So in the previous works, we just consider in the minimum basis, so which is the red curve in the above. And while in practice, we need to consider more complicated bases for the simulation. And in that case, you can see the energy curve are still quite different. So even if we can get the most accurate energy estimation for the minimum basis, still we have a huge gap, a huge difference to the actual energy curve. While in the quantum chemistry simulation, the required number of qubits is related to the number of bases. And furthermore, if we consider the unitary coupled cluster ansatz, the number of parameters is also increasing to the number of qubits and also the number of bases. Here, I just quickly estimate the number of qubits and number of parameters that we need to in the optimization. So here, for example, for the minimum basis, without any reduction, we need 4 qubits. and we need 272 parameters. While for the most complicated basis, here we need 200 qubits, and we need 2 billion parameters to optimize. While I also calculate the number of terms in the Hamiltonian by using the open fermion package. So I just calculate the 4 bases because with the larger bases, the number of terms are larger and the computation time is very long. So for the CCPV-TZ basis, you can see we need more than 100,000 terms in the Hamiltonian. So it seems that to get the actual ground state energy of the Hamiltonian here, even for hydrogen, we need more number of qubits, and we need to optimize a lot of parameters. So to summarize, error mitigation works quite well for shallow circuits and chemistry simulation. While on the other hand, to get some very accurate results of chemistry simulation, we indeed need to consider a large basis, while this seems to be still quite challenging. There are a few potential solutions to this problem. So the first one is probably we can try other encoding method, for example, the first quantization method, where the number of qubits doesn't increase with the accuracy, because we just consider directly the wave function of the space. And this method is recently discussed in this IBM paper. And another method is also introduced in the IBM paper. They consider Hamiltonian reduction. That is, probably there are some redundancy in the Hamiltonian. For example, for the minimum basis of the hydrogen, we can reduce 4 qubits to just 1 qubit using some Hamiltonian reduction. But I tried the algorithm, but it seems that the reduction doesn't work very well. So it seems to just reduce at most 2 qubits for larger bases. So another possible solution is to try hardware efficient ansatz, which is also recently realized in the IBM experiment paper. So instead of using the unitary couple cluster ansatz, we may try some other ansatz that is more experimentally friendly. And the final one is probably we can try some other optimization method. So before the end of the talk, I just want to show some results that is done by last week. So it may not correct, but I just want to show you, and to ask for your advice, comments, and yeah. So here we consider the problem for the helium-hydrogen Hamiltonian. And remember that originally we need to solve the ground state energy for this Hamiltonian. But instead here we consider another a tunable Hamiltonian. Here we have a parameter t that we can control in experiments. When t equals 0, we have a Hamiltonian, which is very simple, just this Hamiltonian that is just has local terms. So we can analytically solve this Hamiltonian. And then with the t, by increasing t from t equals 0 to t equals 1, we just recover the original Hamiltonian. So this idea is similar to adiabatic quantum computing. So here, we just solve the ground state energy for t equals 0 just by analytical solution. And then we gradually change t, and then we can gradually get the correct energy curve for the original Hamiltonian. And I also estimate the energy gap between the ground state and the first excited state for a certain distance. And you can see that the gap is still a constant, at least for this simple example. So in general, this algorithm should be analyzed in more carefully to study its energy gap after considering scaling of the qubits and so on. So, okay, so this is a group photo, and thank you very much.
So, thank you. So, questions? Plenty of questions, yeah. Yeah, so I'm just wondering, with this active error minimization thing, I have this error parameter that I say I can tune it, I want to tune it to 0, but I can't tune it to 0, so I tune it to some cutoff, and then I extrapolate back to 0. Now, if I'm in the lab and I'm doing, well, not me, but somebody else is doing a real experiment, then they don't necessarily know what this error parameter really looks like, and usually they have multiple knobs which they can tune to try to improve their circuit, so you're not entirely sure that you're going to go back to 0 with the same, like at the same time with the same knobs. How can you extract a single epsilon parameter that I can take my energies from any method I have and extrapolate them back to 0 and have a good guarantee that this epsilon parameter is a faithful representation of what I have? Okay.
So, in fact, there are two realizations of the linear extrapolation method. So one is you just proportionally increase the error rate. So in that case, you need to know that, for example, for the 2-qubit gate, you have this error, and then you can just increase error. For example, you just run the 2-qubit gate for a longer time to proportionally increase the error rate. But if this is not possible in practice, then there is another way. So in that way, you need first to perform process tomography to the gate, and then with the process tomography, so we can apply some extra poly gates at the end of the circuit to effectively increase the error rate.
Okay, thanks.
Okay, so I actually tend to agree with your sort of arguments about the scaling of unitary coupled cluster and why it's not well suited to near-term devices. But I just want to make a comment about this because I've noticed several talks and actually papers recently which seem to have a common misconception. The proposal has always been to run classical coupled cluster in order to understand, say, what transitions are symmetry forbidden and so forth. And so, like in several papers I've seen recently, people say things like, oh, molecular hydrogen, there's several thousand parameters, and at 10 qubits, it would be 10,000 parameters or something. So for context, LIH has 12 qubits. There are 7 parameters when you run classical coupled cluster. So that's sort of an important part of that. And in fact, it always has fewer terms than the number of terms in the Hamiltonian and not the other way around. Okay. All right, I'll pass to Garnet, who probably has a real question now.
Yeah, sorry. I also wanted to make, I guess, not a question, but a comment, which was on the use of kind of larger basis sets to approach accuracy from that perspective. Like, while that's true in general, I think if you follow the traditional path of classical quantum chemistry that many of us follow, I think in early quantum devices, you're going to want to use qubits a little bit more parsimoniously than that, and that you reserve them for only the parts of the space where there's strong correlation. So that even if you use, say, a CCPV5Z basis with 220 basis functions, the strong entanglements may be only happening in, say, 4 or 8 of those orbitals, and the rest can be treated perturbatively to high accuracy, which is kind of the standard approach for things like DMRG and others right now. Mm-hmm. And I think that's probably the approach you'll want to use on a quantum computer as well, rather than attempting to treat all of these nearly classical orbitals using your quantum qubits.
I'm sort of adding to this, but making slightly disappointing. There is unfortunately an error in the counting of parameters that you're using for the coupled cluster theory. So the exact parameterization for H2 only scales quadratically with the number of qubits because you only have 2 particles. So the number of parameters is equal to the number of particles multiplied by the number of qubits. So it's actually, because classically that's a similar, the number of parameters you have is much larger than the Hilbert space size. Classically that's a simulation which runs in a second or something, and that's because you don't have so many parameters for the exact solution.
Sorry again. Yeah.
In chemistry, usually you're targeting a particular sector of Hilbert space that corresponds to a fixed magnetic runover or total spin. These error mitigation schemes under D4, I think the D4 doing noise simulations, can they take that knowledge of the targeted sector of Hilbert space that you want and then incorporate that information into further improving the error model?
So here, the simulation I just consider for simplicity the depolarizing channel, but in practice we can have an arbitrary quantum channel, and so the error mitigation method works for general quantum channels. Is that the answer to your question?
Well, generally it doesn't take into account the fixed symmetry that you're targeting maybe in the simulation.
You mean the asymmetry of the?
For like, if, let's say I would like to look at hydrogen in the singlet state. I want to make sure that the quantum computer is giving me back singlets and not some mixed state first.
Sorry, maybe we can discuss in private. Yeah.
Okay, good. So any other questions? Is there one over there? Yeah.
I have a comment to make about that last question. I have actually looked at the lithium hydride curve, and it's not actually, in that case, it's not actually a mixture of spin states. It actually comes from at the equilibrium distance, it's an ionic state, and at the separated distance, it's two neutral radicals. And so you have a portion in the middle where there are two states, singlet states interacting, and so you don't have a clean, strongly dominated state, and because you can't run for enough, you don't have enough depth on the current system, you can't deal with those correlations properly. Okay.